Log on, tune in, find out. Another good idea from Cambridge.
Presenter is Madhav Marathe. He's from Virginia Tech, and he's going to be presenting also some emergency evacuation type simulations. Again, very large scale and very detailed, down to the very detailed level of each person and their decision making. So.
Thank you very much, and good morning to everybody. Let me just thank Bruce and Barry for inviting me here. Wonderful place. Finally, the sun has come out, so hopefully we can all get to go out. I'm going to talk about work that our group has been doing on building simulations to support policies and informatic tools for understanding socio-technical systems. So I want to make two disclaimers to begin with. First is this work is not something that I've done alone. There's a large group of us who used to be at Los Alamos before and have since moved to Virginia Tech. I marked Dick Beckman because I heard a lot of Latin hypercube sampling yesterday. He's the same Dick Beckman who has worked with Mike McKay and Conover and has been working with us for 15 years now. And some of you also know Chris Barrett. Folks from Los Alamos certainly know them. Both been there for a long time. So this is a team that a small projection because everybody can't be there. I've figured out to take a picture at the same time in the university. So the talk, as I said, is on understanding socially coupled systems. So what do I mean by socially coupled systems? I mean that these systems are systems in which human element plays a big role, and the individual are coupled with each other as well as to the infrastructure that supports them. We're going to primarily talk about socially coupled systems that support working urban systems such as the public health system or the transportation system or the wireless networks or communication networks that are around. And essentially what we are faced with is a system of system representation. And what makes it really hard from our standpoint in trying to make models for them is first that there are multiple scales in it, and you couldn't have given a better introduction than Barry's initial part. So I'm going to try and touch on almost every point you make here, hopefully reinforce the things that you said. You couldn't have done it better. So first is multiple scales in terms of time and space. There's inherent stochasticity in the system that is extremely important to model. The part that I think was not mentioned and I think very important in this particular situation is what I call co-evolution of these systems. So it's a little bit different than coupled systems itself, but essentially what happens is that the dynamical processes, the interaction network, and networks are a very important part of this, and individual behaviors all co-evolve. And let me give you an example, and I will play this example out again later on. But think about an epidemic that goes through an urban region. If the epidemic went through with no changes in anything, then it would be fairly easy to control it potentially. And a simple control strategy is, of course, for everybody to stay at home. It's a degenerate strategy to control an epidemic, at least the one which is aerosol borne. But what happens is that as the disease breaks out, individuals perceive the disease and make individual decisions on how bad the disease is, and it's based on information that they have collected through local and global sources, and they change their behavior. The behavior change might be either not to go to work, use face masks, get antiviral treatment, so on and so forth. But what this does essentially is it changes the interaction network, the social contact network, which then changes the way the disease would flow on this. So think about disease as a flow field, and the flow essentially changes on this network based on the individual decisions, which then changes the network, and so on and so forth. So this cycle keeps on going, and this modeling this makes it a very interesting problem technically to deal with. The kinds of networks that I will talk about today are large, and that sort of distinguishes the work that we've been doing from some of the other pieces of work. Moreover, these networks are not given to you. I was actually trained as a computer scientist. I'm a theoretical computer scientist by training, and whenever I used to start my research, we used to always start by saying, let G be a graph, and then you solve a problem. What I found out is the hardest part is this first part, which is let G be a graph. It takes a long time to make this graph. There's no information that is available to make this graph, it's not given to you. So we have been using a number of different methods to fuse information. Dick has been playing an important role in building this out in a meaningful way, where we can then actually apply some of the techniques that you would want to study. The networks are very large. We now can routinely study networks of the size of Chicago, which has 10 million individuals and 500 million edges, and they're very unstructured, right? So the key part is these networks are changing in time and unstructured. So the classical methods physicists have developed, which are really very cool, which try and do dimension reduction, such as renormalization group, simply don't work in these particular settings. At least we do not know how they work, and maybe we will find symmetries in these networks over a period of time, but right now we don't know. And finally, the design space is very large. It's again a single run we can now do fairly fast, and I'll show you how fast. It's this large space that we want to explore that makes the problem harder. So let me give you a little bit of history of how we started doing this. The work started back in 1991 or so in Los Alamos. There's a project called Transim. Some of you might have seen this before. It ended approximately in 2001. It was funded by the Department of Transportation. It lasted for a very long time, and in my opinion was one of the first agent-based modeling environments to study social systems at this scale and use high-performance computing to enable such simulations. This was done after the EPA Clean Air Act was passed, and people found that the classical methods, the classical four-step methods that were used in transportation modeling in world were simply not working very well in terms of understanding and reasoning about large-scale traffic systems. If people have eventually found that these systems are chaotic, and I'll leave those results here for now. But what happened was that it made it very clear that you need to use a multi-scale and a multi-model environment in which the dynamics have to be represented in far better way than that had been done till then. The second part that Transims did was it used the concept of activity-based modeling, which meant that you do not use a statistical model to fit to the data that you've gotten, but try and use some sense of why people might be going where they are going, because then you can study questions like, if a bridge were to break, or if I were to add another lane, how would the traffic change? Here was a very classical question the traffic engineers faced, which did not have a good solution. You measure traffic on the road and you realize that, let's say there are 500 cars per hour moving on this road, and let's say there are only 3 lanes going in that direction, and maybe that's not enough. So they decide they put a 4th lane in. The problem is that, and you can make some prediction of how many people would change, but people change their behavior when they are given this extra choice, when the traffic actually reduces. So a lot of people who never went by that road now start taking that road, and very soon you find it filled up, and this has been going on and on across the world, where we keep on adding lanes and the traffic keeps on increasing. So the toll system that was put in place in London is a way to control it, of course, and it's worked reasonably well, as I understand, but you folks can correct me. So Transims actually was a successful project in some ways. It started as a basic research program, went all the way to deployment. Department of Transportation continues to fund it at some level. Argonne National Lab has an open source license. It's changed somewhat from the times we left, but Argonne has an open source license for this, and folks who want to use it can use it. And I have a nice visualization made by the National Supercomputing Center at Illinois that was made, and I wanted to show you this because it gives you a sense of scale that the system deals with. These are cars moving on the road, and I think very nice graphics that they built out, but essentially you get scales in which time at the final level of a micro simulation of car interaction is roughly 1 second, and the spatial scale is 7 meters, all the way to activities people do over 6 months to an year basis. So you're talking about scales in which cities span, a city of the size of Chicago, and down at the level of 7-meter grids and 1 second fidelity. And fair amount of work has been done in doing validation, and that's the purpose that I want to speak here, and I'm hoping to get advice and suggestions from you folks. We have done classical ways to do, what people would call validation. The classical ways of fitting data to observed behavior has been done quite a bit. But I would argue that systems like this, that's really only one part of validation at all. And we need to understand what's called structural validity, and we also need to understand the usefulness of a model in this particular setting. Simply matching the data that was given, and we did that. So for instance, in traffic, we made sure that the population densities are matched correctly, the block group level densities are matched correctly, the surveys on movement patterns of folks is matched correctly, traffic counts on the road, measured roads are done correctly. All this thing is matched, but I think the part that makes it more interesting is to use it in a counterfactual way, because after all, this data set is only one accident that happened in real life, right? I mean, many possibilities could have happened which did not play out, and giving undue importance to just matching it doesn't seem to make that much sense, in my opinion. So the goal is then to talk about validation verification to the extent I can in the time I have, and I'll try and focus on structural validity as well as adequacy. The representation we have used are what I would call individual based, which means every individual in the city is represented. So in Chicago, 10 million individuals are represented individually, and they interact on a interaction fabric, the network. In this case, I'm talking about epidemics, that is going to be used as an example. I'm going to talk about social contact networks. So the issue is, why do we need models of this level of detail, right? Can we not do something with models that are much more aggregate? I'll try and at least give you some sense for it, and I'm happy to hear other comments that you folks might have at the end of my talk. So what I'm going to do is, the remaining time, in the next some minutes, I will describe the system called Simdemics. It's a modeling environment that we've been working on for the last 10-11 years now to understand and support public health epidemiology, an outbreak of infectious diseases in large urban regions. And then I will talk about a technical issue on validation to connect it as one example of the kinds of questions we face. I will mention a few other questions and hope to talk to you at the end of this period during our coffee break. So Simdemics is a high resolution modeling environment. To give you a sense, before we started doing this work, and actually there are other groups who do this now too. Neil Ferguson at Imperial College has done excellent work as well. Matt Keeling and his group at Warwick is doing very good work here in England, and there are other groups as well. But by and large, in epidemiology, the class of models that were being used before were called mean field models or mass action models. They basically said that population can be divided into finitely many bins or groups, and the simplest one is the SIR model, susceptible, infected, and recovered. And you write rate equations on how there's a flow between these states. Number of folks who become infected starting from susceptible depends on the product of S and I, and then the people recover at a steady rate depending on the disease itself. You can have SIS model, SIER models, and variations. But all of them basically use a finite set of groups and interactions and a flow equations between them. And the direction we have taken is to try and use a network-based representation to argue that epidemics, after all, spreads at least aerosol-borne diseases to begin with, but the same holds for other diseases. I'm going to talk about influenza through social contacts. People come in proximity and they spread diseases to each other as a result of that. So we would like to represent this explicitly, individuals and their interactions and their proximity, and then derive the epidemic process on top of this time-changing network. We've argued, and I think reasonably well by now, that this methodology is useful in certain cases. This doesn't mean that the aggregate models are useless. In fact, they've been very successful in the past. But I think these models allow you to study kinds of questions that are quite different than the questions people have studied in the past. Moreover, what they allow you to do is, in fact, do data-driven discovery of certain kinds of interventions that would not have been possible in the other case. And I'll hopefully be able to give you examples after we're done with this. So the basic environment has 5 steps, It starts by constructing a synthetic population of a city or a region that you so desire to model in a way that individual occupy houses and households are there. And the key is that these are synthetic individuals, which means the privacy and anonymity is preserved. But if you do any aggregate measurements on this population, they look like the census that has been given to you. And it doesn't have to be a census. More and more data is available through other means, and you could take those distributions to match it too. So essentially the whole work in this step is to take aggregate marginals and construct disaggregate individual elements such that when you take the distributions back, the aggregates match up. So in that sense, they are they're validated, or they respect the data that they started with. And again, this work was done in a very, very seminal paper in this part of research by McKay and Beckman, and it was published in Transportation Research. Used very simple statistical techniques, but made a very nice application. That's what Dick seems to be very good at. He uses very simple ways to do something nice. The next step is to derive a social contact network. We use survey data. We use data from places like Dun and Bradstreet, data from Axiom, many other data sets that allow you two things. Tells you the locations in a city, all the built out infrastructure, schools, colleges, hospitals, houses, buildings, and this is available actually for a price. And you also use surveys from the Department of Transportation. There is actually a survey that is being collected in UK too about the movement patterns typically that people have, and they use both of these pieces of information along with some behavioral models to assign individuals to locations and construct a social contact network. I'll do a little bit of detailed discussion on that. We then assign individuals what's called a disease model, and this is basically a model of how the disease would evolve within an individual. As the individual starts being a susceptible individual, becomes infected individual, recovers, and so on and so forth. You then couple this to a dynamical process, individuals interact, and that's how the state changes within this. If you think of this as a extension of a finite state machine that the previous speaker talked about, but it's called a probabilistic time transition system. That's a better name for it, because the transitions in this automata are twofold. One is they are transitions by interacting with other automata, and they are probabilistic, so they jump with some probability to the next state. But they are also timed, which means when you are given state, there is a timer. For instance, when you are infected, you recover at a certain rate, and that's why you need a time transition system rather than a simple finite state machine. And then you study using decision processes and game theory effects of interventions and coevolution. So these are multiple models that are hooked in place. People have asked me, what is the model that you use? Turns out there are many models that are hooked together in doing this, and the scale changes and sort of speaks to the point that you made before doing this. I wanted to put this slide because we've been doing this in conjunction with practitioners, and this is something that we have tried and do our best, because we have found out that we can keep on adding new features to our models, but the models are best used and accepted by the community if you work with the community in doing it. So I have a bunch of examples for the traffic or the transportation part, which I have not put in, but let me describe the kinds of studies we have done over the last 10 years or so for epidemic public health modeling. And one of the first studies we did was after the 9/11 incident, and there was a serious threat for a bioterrorism event in the US, and there was a paper by Larry Vine and his colleagues in PNAS which argued for mass vaccination in case of a smallpox attack. Now it turns out that smallpox vaccinations are not given in US on a regular basis anymore. It's viewed as eradicated, so you don't, unlike for me in India, they still used to give me shots. I don't know what happens right now. But what's the problem with that? The problem is we do not know the side effects of this vaccine given to a 40-year-old who might be immunocompromised, because we have not done this. So there's a real fear about causing more harm to society by allocating these vaccines than to try and defend yourself in some other way. So we were able to argue that if you actually do what's called quick discovery of the spread followed by targeted interventions, you are likely to do better than a mass vaccination campaign. The only problem with this result was that early detection, how do you do early detection remains an open question still, and we are working on this and everybody is. And what sort of targeted vaccinations do you do? We did an optimal algorithm to do it, right? The problem is the following. This optimal algorithm picks up a set of people whom we think when vaccinated would stop the spread fairly well. They're super spreaders essentially. What is the problem is that these are identified only in our simulations. They do not have a description in a normal demographic form that would allow us to run this campaign very well, at least when we did it then. We have now found new results which were able to correlate this, essentially a data mining exercise. You look for people who are likely to be best set for vaccination, and then convert it into what's called an implementable strategy, in which you look for demographic attributes that best correlate with this particular feature that we call vulnerability or criticality of an individual. So that piece of work is actually something that goes on very well with this discrete modeling. Let me take one more example and then I'll move on. We work with Neil Ferguson's group and Ira Longini's group as a part of a Midas project when the H5N1 scare was around, and this led to a concept of targeted layered intervention, TLC, and it's become a part of federal pandemic influenza plan, and since then has also been put as a planning document for WHO, and it basically calls out for layered containment. You decide when to put social distancing in place, when do you put stronger and stronger forms of intervention in place as the disease outbreak happens. And this was actually a rather interesting study where three different models were docked together, quote unquote, where as in simulation world the notion of docking means that you try and see whether the models are doing similar things as you go along. We found similarities and we found differences too. If all the models always said the same thing, then maybe there's no use of having these three models anyways. But I think this study really pointed out to having different viewpoints on the same system and trying to understand if they are trying to argue about certain policies in a similar direction or not. One of the other things that this study put forth is the need to provide a tool that works rather rapidly. When we did this was supposed to be 1 week exercise because there was a serious issue that they wanted to solve in the emergency planning office in the federal government. It finally took us 6 months to do this, and it's always the case. Which seems easy, it takes time. The last one is actually interesting because we've been working with the DoD to do military preparedness, and it turns out that a general goal of public health epidemiology is to potentially, and I'll say it in a way that might not sound very good, but sacrifice a few to save the many is the issue. At the end of the day, you want to make sure that the population is safe. But when you talk about small critical populations such as the military or people who are working in the government or people who are power plant operators, doctors, the goal is really to protect these small set of folks, and the ways that you do this is potentially very different, or the strategies you would use is very different. Again, a standard strategy is to do sequestering, right? As soon as you hear about the disease, you pull them in a place and essentially don't let them interact with others. The problem is it's not a strategy that works very well, because every time you hear about a signal, and there are a lot of false positives, you would pull them up in a base and then this is not going to work for long. So you decide when this has to happen, how many casualties you expect when a situation like this happens, and so on and so forth. So there's underlying mathematical theory that we've been building in parallel, and I will only talk about it in 2 slides, and hopefully we can talk about this during the break. We call it the graphical dynamical systems. It is akin to graphical models people use in Bayesian inference. Okay, and turns out that many of the properties that we study here have interesting applications to that world as well. So I wanted to flash this slide only because I'm at Cambridge, and next year is the centenary celebration for Alan Turing, and this work is really builds on all the work that has been done a long time back, of course, but we show that this mathematical model is actually very powerful from a complexity theory standpoint. we can actually formally show that graphical dynamical systems are very powerful. They can simulate traditional Turing machines so that you don't lose any modeling power, and then you do what's called dichotomy theorems that give you tight bounds on when problems can be solved easily or are very hard or intractable to solve in a provable manner using the theory of computational complexity. So I'll go through these steps fast. So I just jumped through the individual steps. Let me take a minute on this slide because I think it will tell you an answer to the question or the issues Barry posed. When we started doing the simulations, one run used to take us a long time. To give you a sense, in around 2004, to do one run of a stochastic simulation on a 40 processor machine for a population of Chicago, 10 million individuals with 500 million edges, would take approximately 40 hours. You've done a fair amount of work on algorithmic side, and today we can actually make one run in 40 seconds. Okay, so and you can take off some factor of it because the speed up you get from the machines for free, but I don't think so. It explains all the speed up one gets. The last column is actually a different kind of simulation, so it slows down a little bit, but allows you to do what's called interactive simulations. You can start and stop it, and so you can play out a potential intervention as the simulation is evolving. And talking about control and decision making that the previous speaker talked about, this is a simulation that is useful. So high performance computing is at the heart of doing this work. We've been able to put it on big machines. I'll quickly talk about it. We have built an interface so that naive or policy makers who are not computational experts do not have to use the model in a way a computational expert uses it. And this is a interface that was designed, and again Dick played a big role, and essentially this GUI forces a person without them realizing to design a factorial experiment. Okay, we can of course make it more sparser designs, but essentially it does that, and it is doing it in a way that a public health analyst feels very comfortable. He is asked, what sort of region do you want to simulate, what sort of disease you want to do, what sort of interventions do you want to do, and in doing this it also says, well, how many replicates, how many total cells, and it will give you a sense for how much time it will take. But in the end, the person is really nudged into doing a design without he or she knowing it, and you get actually outputs that again are scripted, where you can get standard plots, epidemic curves, which are built out, and then you can also get the file for detailed analysis. So for most part, a person at NIH or DoD doesn't have to worry about the HPC machines or the model details once they believe in it. Of course, they can run it directly. The last study that I talked about had another thing that was done with it. We found out that if we have to do a study every time along with these end users, then it becomes very taxing for us and also not meaningful because they want to do it themselves at the end of the day. So what we have done in parallel of the modeling part itself is to build a cyber environment. It's a pervasive computing environment that allows you to deliver these results without having direct access to the machine. So right now the situation is this. There are 4 or 5 clusters. We have 4 clusters that we own, and the TeraGrid at NSF and DoD clusters that can all be accessed through our platform, and the analyst essentially puts out a design through this interface that I showed you. The data is picked from one place, the right computing resources are picked out, the things are run either in the Albuquerque Air Force Base or at Virginia Tech's parallel machines that we have in our group, or at the NSF TeraGrid site, and the results are brought back to the end user without him ever noticing all that happened at the back. Okay, and this was really important for us because now they can actually do these studies. Otherwise, we found out for Transim, that was part of the failure for Transim. We built these models, but we had to work with the end users every time, and so acceptability of the model in terms of day-to-day use certainly decreased a whole lot. This has completely changed the model's usage on a day-to-day effort. So I had a number of movies. I'll skip through them and very little time, but I want to at least pose one question on network sensitivity because that's the focus of this talk. The issue is this: in the current literature, in general, people believe that there are the standard random graph models or network models that are fairly good to understand realistic systems. They started out with early work by people in physics who said scale-free networks explain many of the features and properties of real-world networks. We argue that, and the scale-free network is scale-free, the degree distribution is scale-free, which means that the degree distribution obeys a power law. It turns out that this is really not adequate for the kinds of system we study, and what we have done is we have tried to create a methodology in which we can understand the sensitivity to network structure and understand when certain structural features would be important and when they would not be. And in a nutshell, the way this works is it starts with a, this is the space of all graphs, this is the space of all scale-free graphs. Our real-world networks are a very small fraction of this, but we do what's called a switch operation. A switch operation takes 4 nodes, looks at the edges between them and swaps them. Okay, it is a way to do perturbation on networks in a way so as to preserve certain structural features. If you use standard perturbation theory that has been done in matrix theory, it doesn't work quite well because these perturbations are not random. We want to maintain certain structural features. So the degree preserving perturbation is a perturbation in which you take 4 vertices, the 2 edges, and swap them. This would preserve the following: it will preserve the degrees of all nodes before and after the operations. Okay, you can do perturbations which are called assortativity preserving, which means the labels are right, or clustering preserving perturbations. The point is, if you want to say degree is an important parameter and explains most of the results, then you start with a network that we call a realistic network, do these perturbations or called switches, and it's actually a very well known result by Claude Burge, which says that by doing this local transformation you can actually walk the entire space of all the graphs in which the degrees are the same in each node. But turns out that if you start with such switches, you do not maintain the dynamics in a manner that you would like, and maybe I'll show you that result here. This might actually do the trick. The right graph is a graph in which you look at the outbreak size. It's called the epidemic size in a network, is a function of the number of edges that are switched or changed. In a manner, in this particular case, you preserve the degree distribution. Why is that? Well, there is a classical model of random graph called Chung-Lu model. It's a model to produce a graph with a given degree distribution, and there are analytical theorems which show you that you do not get large epidemic outbreaks on these scale-free graphs modeled using Chung-Lu model or a configuration model. The problem is that result doesn't apply, and it actually shows very well in this particular plot. The green line is the outcome of the flipping on a Chung-Lu graph. Since the graph essentially is a random graph, these flips really keep it in the same space. On the other hand, if you look at the graph that we started for Miami and you do these flips, you can actually see that you start with a completely different distribution of epidemic size to begin with, and it slowly converges, starts looking like a Chung-Lu graph once you have done enough walks. Now we do not have a mathematical proof whether this samples graphs uniformly at random from the space, and that seems to be quite hard to do. And I'll stop with one last slide here. The slide on the right actually makes a very important point in terms of policy, which says that if it is the case that the dynamic, so first is the Chung-Lu graphs are different than the network that we have, although both of them have a power law part of the degree distribution, but they do not have other structural features which are similar. Clustering coefficient is different, shortest path distribution is different. So you might argue that, well, it really doesn't matter so far as the dynamics you get on the graphs are similar, in which case model is wrong, but the dynamic part of the result is right, and we talked about it yesterday. Maybe that's okay. Turns out the dynamics is not right too. The previous slide had the epi curves. You might say dynamics is wrong, and still it's okay if my policy questions that if I decide on a certain ordering of interventions, that comes out okay. I'm still sort of okay, right? My model is wrong, but at least I can say the right things as far as policy is concerned. And you would expect this not to happen, but this plot makes a very good case. The left side is a result which has no shuffles, okay, which means you start with the network representation we had, and it tells you how you get different efficacies from interventions: school closures, vaccinations, work closures, social distancing, and how the ordering of these things changes as shuffling is done. And I'll stop here in the interest of time and take questions.
answering the questions.
Okay.
Our coffee break is supposed to start at 11 o'clock, so I think we have a little bit of time for discussion for both of the presenters.
I was very intrigued by the form that you had clients fill in where they unknowingly designed an experiment. I was wondering whether the actual experimental design that you end up with is, however, sufficiently robust against variances in the variability of the assumptions, which might need to be valid in order for the design to actually give results that are really useful to the customer. Do you actually ensure that any sort of implicit assumptions, which perhaps the client has not been asked about, are also handled properly?
So I think it's a very good point. I mean, if you hand this over to a person who wants to abuse it, then it's certainly a way to do that. But our experience so far is that if you train them, and we have had training sessions in our place, Dick will give a 1-hour tutorial on how to use this. They understand it reasonably well. So the probability that they make absolutely naive errors decreases substantially. Now we have gone back and tried to bound the region in which they can do certain. So vaccination strategies, you can choose extremely drastic strategies, but when you give it out to a certain class of customers, we would control it into a regime that makes sense. So there is a certain amount of work that is being done by us, but at the end of the day, they can still search the space rather than us doing it, changing the files, configuration files every time, making runs, making the plots and giving it to them. So yeah, it's a very good question. I think it can be misused, but I think we've tried to do as good a job we can currently do. We're trying to improve it further also. I mean, this is not the end of the work at all. This is really a beginning of the step. As we get more feedback, I think we'll do better, hopefully.
And I ask you because I did quite a lot of work for Eurocontrol, and that's the air traffic control safety people, and designed experiments for them for real-time sort of simulations, which were extremely expensive. And we came up with what we thought were quite clever designs, but then when they looked at it, initially they were impressed, but then this was, but what happens if some of our assumptions are incorrect? We might end up with carrying out very long, expensive experiments and end up not being able to actually come up with any sort of good analysis because our assumptions weren't actually properly matched. And your tool sounds as if it might have been a very useful one to have had for to help in the design.
Clothing, right. Yes. So it just turned out that we're working with the Gates Foundation with the Swiss Tropical Institute, and we're doing other work for them to do this infrastructure. But they really like this interface. So among all the things that we're not supposed to do, they really wanted this design thing to be put in. But I can sort of relate to why that was the case. We tried to do it to make our jobs easy, actually. We didn't want to do these studies over and over again. Yes?
So my question definitely bumps off of that one and might even be a repeat. So my question is along the lines of assumptions, and obviously these people, as they design their experiment, the inputs change, your outputs are going to change, your results are going to change. So along the lines of assumptions, there's what you have coded, right? You have made assumptions within that code, and possibly this is too much of a question to answer now. What assumptions within that code do you think are most sensitive to the outcomes?
Right. I think that's a good point, Liana. That I was heading in that direction with the network sensitivity work, right? So the graphical dynamical system provides a very clean way to abstract out. So there are essentially 2 or 3 elements. There's a graph, and there are local interactions, local functions. And the outcome is sensitive to both these structures. And there are multiple automatas at each node. You know, there's automata for different behavioral regimes, and there's automata for disease transmission, and there's automata for adaptation. Similarly, the network comes in different forms. So the network sensitivity work, there is a couple of other papers that I couldn't show, is our effort to try and understand the assumptions we have made in trying to build these networks out. And again, we are really at the start of this game. I think the sensitivity analysis for large agent-based models is a really open question as far as I see, and I can say that with a little bit of confidence in front of you folks, because I asked Dick, can I say this, Dick? Do you folks in the statistics community just throw me out? And he said, no, I think, Madhav, that's a fair question to pose for the community.
So what are you doing for sensitivity? Are you just looking at epidemic curves, or what exactly are you trying to detect when you think?
So we are actually looking for a number of different what's called measures of effectiveness. Epidemic curves, the time to peak, the height of the peak. These are standard ones that epidemiologists always study. But we also study things such as number of school kids falling sick, which is very different than what they usually do in their setting. So epidemic curve for small subgroups. We can also look for things which have to do with spatial part of it. Do you see the disease break out in one part versus not in other part? And then we do some basic, what we'd call physics-like validation. We would make sure that when you're given scale-free graphs like the Chung-Lu model, then it produces the kinds of epidemic curve that analytical results would try and predict. So, which has so that's a verification part, or giving us confidence in the implementation itself. The modeling part has been done by looking at various surveys, and I can show you later on. There are three more things that I never reached at the end of this period. So I certainly be happy to talk to you. But it's an open field. I don't think so this is done really at all.
I had a quick question on your interactive. You said that you had an interactive mode that you could run that simulation in and you could stop it. Is it possible to stop it and then freeze that state so that you can then run different scenarios from that state, or is it once you've moved on you've lost the state?
No. So the first version you can just stop it and then you can analyze. So it's a situation assessment and then go forward. We were asked exactly this question, so we're building in a way to store this, but you can see that the tree starts branching a whole lot. Mm-hmm. So if we do this well, then we would allow a limited amount of branching in this tree, and at some point we'll have to say that we cannot branch anymore in some form, so and that would be a user-specified parameter. That
it sounds like a limited split plot experiment for those people.
Yes, please.
Yeah. So a number of these elements of the model, actually in both talks, were elements of human behavior that were coming into play. And I'm just wondering, what's your experience in terms of actually fitting human behaviors, given that it's very hard to measure human behavior? For example, school closures you might be able to do very in an authoritarian way, but vaccination, there are a lot of assumptions about how much it would cost to vaccinate a various fraction of the population. A certain fraction would never want to be vaccinated.
Absolutely right. So compliance is a big issue. Targeting is a big issue. Efficacy is a big issue. So maybe this is still work in progress for the entire epidemiology community, not just for us. Having said that people do measure through either surveys or now through crowdsourcing like environments. People would be given these games and study, as previous speaker talked about, data on certain classes of behavior that people might undertake. And these models, I would not argue that we are the best folks to decide what behaviors people take. I think this environment tells you how to use a given data that is available and to look at its composition across multiple fields. So if the question is there good data for human behavior? I think depends. Certain cases there is, in certain cases there isn't. And always surprises happen. So for instance, a rational behavior would tell you that when Katrina came around, people would have left, but so many people stayed back, and this has been observed over and over again. There are some people who do not change their behavior for different reasons. So people are collecting information about how people would behave during crisis, which is different from the normative behavior people have. And as this data becomes more and more available, this kind of environment will allow us to ingest it better rather than not make use of it.
But is that data reliable? I mean, if you ask someone how they react,
that's a good point. Absolutely right. If you ask somebody, you might say, yes, I will certainly evacuate. And the day the evacuation happens, you say, no, my house is too precious. So yes, there is certainly an element of error, and that's why that's why it has to run very fast so that we can do a big range of things. And this remains a really big open question, how to do sensitivity analysis over this range. Because think about, so this is a question that me and Dick have been talking about for a long time. In just the disease model, there are two parameters that are numerical, so they take 4 or 5 values. and even assuming that everybody has the same disease model to begin with. And one of the parameters is a distribution parameter. Now the question about how to do sensitivity in which you draw from this distribution for 10 million agents and say something about it is really a hard problem that we still are grappling with, right? To find out the nodes which are most important, the nodes in which this distribution has to be understood better. All these questions remain open, and you folks, I'm sure, have studied it in here. But the size really makes it for an interesting research direction, in my opinion.
Okay, let's thank Professor.